Hello and welcome everyone to today's webinar on integrating Kubernetes applications with your networking pattern. My name is Tara Van Cleve and I'm a marketing event manager for the developer initiative here at Oracle. We're excited to show you an efficient and reliable way to deploy OKE to your cloud network infrastructure as we cover networking best practices and demonstrate how you can set up networking for OKE. If you do not currently have an Oracle Cloud account, we've got a special promotion with extra credits so that you can try out the services and follow along with the demo today. To access the promo, please sign up using the same email you registered with for today's event, and I'll drop that in the chat in just a moment. We'll also be recording the session, and the link to the recording will be sent to you via email in the next couple of days. If you have any questions during the webinar, we've set up a channel in our developer public Slack called Oracle Kubernetes Webinar that you can access at the QR code or at bit.ly/odevrel_Slack. Once you're in, you'll land in the general channel, and from there, you can search for the webinar channel. We'll also be checking the Zoom chat and the Zoom Q&A areas throughout the webinar, and we'll also open up for live Q&A after the demo. Today's webinar will be presented by Ajay Chabria, Principal Solutions Architect, and special thanks to Jeevan Joseph, Senior Principal Product Manager, who will be helping answer questions. So without further ado, I will hand it over to Ajay.
Perfect. So hello everyone, welcome to live developer webinar. My name is Ajay Chabria, and I'm a Solutions Architect at Oracle Cloud Infrastructure, focusing on building the managed Kubernetes service. Today in this talk, we will focus on various networking patterns that one can use with our Oracle Kubernetes engine to deploy their container-based applications. I also have my colleague Jeevan Joseph, who will be helping me out with answering questions at the Q&A window. So if you got any questions, please put it in the Q&A window, and we'll also have some time at the very end to go through it. So without further ado, let's go to the agenda. Here's the agenda, and where we'll start off with a bit of network foundations recap. So summary of base building block of the OCI networking overall. And if you're already familiar with those base building blocks, it's going to be much easier for you to translate those components into the Kubernetes world. If you're new into the networking, that's going to be a quick introduction to get you on route with everybody else. Then we'll move on to cluster connectivity, talking about various gateways we support in Oracle Kubernetes. I will talk about the basic building block, the pods, and how they communicate using different CNIs. Then we'll talk about more advanced concepts like exposing services, network security, and CoreDNS. So we're going to spend most of the time in explaining the architecture, traffic flows, and how things are applied together. At the very end, if time permits, I will also cover on how you can deploy things using the Oracle console. So to begin with the networking foundations, here is an example region called US Ashburn 1. And as you can see, this region has 3 availability domains. Think of it like a physical infrastructure on which you will be deploying your Kubernetes logical components. The primary logical component you see here is your virtual cloud network, or what you call as the VCN. That is your private environment. Think of it as a virtual private data center, and you decide what goes exactly into that environment. You decide what that environment communicates with. So the first thing you need to do is to decide the IP address block that you allocate to this particular environment. So in this example, you would typically use like a private IP address block. In this example, like 10.0.0/16. And once you decide on the CIDR ranges for your VCN, you can start subdividing them into subnets. Subnets would be deployed either inside a specific availability domain or even the entire region across all the 3 availability domains in this example. So a VCN spans the whole region, and so could the subnets be as well. Subnets use an IP address block that is a subset of the original VCN CIDR block range. So once you have your subnets, you can start deploying Oracle Kubernetes resources into those subnets. So in this example, as you can see, we have something called as the worker nodes for your Oracle Kubernetes clusters that have been created into multiple availability domains. So worker node 1 is in AD1, worker node 2 is in AD2, and worker node 3 is in AD3. So this is one of the best ways to make sure that you are achieving high availability. And also, as you can see, there is an API endpoint, load balancer, and pods on the top of it. So this is how like a typical deployment of the Oracle Kubernetes resources is done. And all these Kubernetes resources that I spoke about are allocated a private IP address from their respective subnet ranges. Now, this VCN that you see is completely isolated. But what if we want to connect to, say, let's say the internet? And for that, we need to do a few things. So with that, let's focus on cluster connectivity. So first of all, we would deploy an internet gateway, and that's an Oracle managed gateway. Today, Oracle Cloud Infrastructure support multiple different types of gateways, depending on where you're connecting to. So if you're connecting to, let's say, the internet, you need an internet gateway. Now, you would also need to allocate public IPv4 address to the source that is originating the traffic to the internet. So in this case, as you can see, the load balancer at the very center, this load balancer needs to connect to the internet. So the first thing what it's gonna do is it's gonna have a private IP address, but before it leaves for an internet gateway, it needs to be translated to a public IP address. So the next thing you do is you set up your routing. You need to configure a route table that you can associate with any subnets you want to allow this load balancer or even the API endpoints to be able to go to the internet or NAT gateway when they're communicating to the internet. So at this point, let's say the load balancer here in subnet A can talk to the internet, but the internet also can initiate the connection to the load balancer. But what about the worker nodes here in subnet B or subnet C or subnet D, where we don't want the internet to initiate the connection to the worker node? And in that case, you just only want the worker node to initiate the connections outbound. Or you want this worker node to maybe talk only to some OCI services. So for that, we would need to deploy another type of gateways, which could be either a NAT gateway or a service gateway. So NAT, as it stands for Network Address Translation, will be translating the private IP address of the worker node to its own IP address. And NAT gateway would also allow the traffic to go out. But if you try to connect this particular worker node from the internet, the traffic will be dropped. And like I mentioned earlier, there could also be another situation where a worker node only wants to talk to an OCI service and also NAT its traffic. That is when they can use service gateway that will route the traffic through the Oracle backbone without having any internet footprints and just talk to this OCI service. So this is how one would really configure the Oracle Kubernetes resources for their cluster connectivity. Now, let's try to understand the pod networking. So the connectivity that I showed you in my previous slides, the connectivity that we achieved through gateways was mainly for the traffic going north to south. Now, let's understand how traffic will move from east to west between pods inside an OKE cluster. So we recently released a new container network interface plugin or a CNI plugin that will provide pods with an IP address from the VCN CIDR range resulting in the same network performance as virtual machines with no additional overlay required. So this is effectively a pod itself or a daemon set of pod that controls how the networking is done. And your pods, as you can see here, right here, are getting an IP address from the VCN CIDR block. Your pods are routable within your VCN. They are routable between VCNs and even from your on-premises network. So in our example right here, we have a VCN, we have a worker node subnet, we have a worker node, and all of them are running OCI VCN CNI plugin. And the pods, these small boxes, are getting an IP address from the VCN CIDR block. Now, you can also apply other virtual networking constructs like network security groups to these Kubernetes pods to ensure the security for these particular applications running inside the pods. And the pod's IP can also identify the network traffic going in and out of the pods. So for that, you could also use something called as VCN flow logs for auditing the pod's network traffic that passes through your VCN. So now let's understand how the traffic would flow if the pods are trying to communicate between them either in the same worker node or between two different worker nodes. So the way we allocate IP address to the pods is we would have a secondary virtual network interface on the worker node configured in addition to the primary network interface, as you can see. So there is this worker node right here, which has a primary VNIC and a secondary VNIC. Now, as pods gets provisioned on the worker node, they would get the IP address allocated from this particular secondary IP addresses that we allocate to the secondary VNIC. So that is something the OCI VCN CNI plugin takes care of automatically. This way, each pod that gets connected to a VNIC and it's directly hooked up to the VCN. And pods will always get an assigned private IP address from the pod subnet. So if we look at how pod-to-pod communication looks into the scenario, so let's say if this pod right here wants to communicate to this pod in the same worker node, this particular native pod CNI would make sure that the traffic just goes or gets switched right here within the same worker node. But let's say if this pod in worker node 1 wants to talk to a pod in worker node 2, the traffic would be handled by the native pod CNI, and the native pod CNI would determine that this pod is not local to this particular worker node. And hence, the traffic would go out of the VNIC and just be handled the same way as the traffic between the two virtual machines are handled in a virtual cloud network. So the pod eventually on the right would actually see the real source IP address of the pod on the left connecting to it. There won't be any overlay addition happening in the packet, and directly we will be able to see the source identified at the destination. So that was about OCI VCN CNI, and this is another CNI we support in OKE, which is called as the Flannel CNI. Flannel, for those who don't know, is a simple and easy way to configure a layer 3 networking, and it is designed for Kubernetes. And the way it runs is, or the way it works is, it runs a small single binary agent called Flannel D or Flannel daemon on each worker node. And that Flannel daemon is responsible for allocating a subnet lease to each worker node out of a larger pre-configured address space. So this diagram right here, it clearly shows how the packet flows between the pods in two different hosts compared to what we saw in the last slide. As you can see, the packet here encapsulates a VXLAN header. So there is an additional overlay being added by the Flannel daemon to route the packet out of the worker node through the VCN and all the way to the other worker node. So Kubernetes worker nodes, as you know, they run several pods that get their own IP addresses from a private overlay network, which is specific to a cluster. So this extra layer you see in yellow of overlay pod network, that is being built using a Flannel CNI plugin that actually provides the networking at layer 3. So by default, Flannel uses like a CIDR block called 10.244.0.0/16 to allocate smaller subnets with 10.244.0.0/25 mask to each worker node. And then pods uses those IP addresses from one of these subnets allocated to a given worker node. And like I mentioned, Flannel uses VXLAN to encapsulate the traffic in UDP packets for pod-to-pod communication in 2 different hosts. So let's say if your application environment requires you to not use an IP address from the VCN CIDR block, like we saw in the previous example, or the use case is basically you require a high density pod per worker node, then using Flannel CNI is more preferable. Another use case related to would be the density per node is VCN IP starvation. So let's say if you are really restricted in using a lot many VCN IPs, this is another solution that you could go for. So this overlay that we saw about here, right? It frees up considerable amount of IP addresses within the CIDR block if VCN IP starvation is a consideration. So I would want to pause here and see if there are any Q&A. Jeevan, you want me to answer, or are we good there?
There is one Q&A question which I'm answering right now, so I think we're good. You can move on, Jay.
Okay, perfect. So let's focus on the next section, which is called as service discovery. So when we talk about service discovery in Kubernetes, the first thing to always consider is how do we do the DNS resolution, as DNS has been used for service discovery for many years. So when we think about how we are incorporating the DNS of the Kubernetes cluster with the DNS of the VCN, it is important to remember that anytime our pods needs to make a DNS call, it is first going, that call would first go to something called as the CoreDNS, which is a service that is running inside the OKE cluster. That CoreDNS server, if it cannot resolve the request, it will forward that request to the VCN resolver, which is typically an endpoint dedicated for resolving FQDNs inside your VCN. And eventually, if that VCN resolver cannot find anything, then it will forward that request to any upstream DNS that you have. Now, think about that. Let's actually consider what are some of the domain names that exist and where does the authority exist for each of those names. So you may be familiar with the VCN resolver that gets created whenever you create a VCN. There is a VCN resolver that gets created, which has the default name called as oraclevcn.com. Now, CoreDNS, on the other hand, and Kubernetes also creates a new authority that exists, which is called as service.cluster.local. And the authority for these domain names, they remain with the CoreDNS. So anytime you create a new service inside your Kubernetes, that service name, so let's say if I'm creating a service name called as foobar, right? So that service name, which is foobar dot whatever my namespace name is, will automatically register inside the CoreDNS. So let's say if I have foobar in the namespace default, right? So it would be foobar.default.oraclevcn .com. That would be the name that would be registered inside my CoreDNS. And if anything does not fit into that service name, then that particular service name .namespace name .service .local, that would eventually get forwarded to the VCN resolver. So this is how it works, kind of. So this was about how DNS really works in Oracle Kubernetes Engine. Now let's focus on how you can expose your services, your application, using OCI load balancing services. So when you define a Kubernetes service of type load balancer, right here, example. So this is your service definition file for your OKE. And if in your specification, you say that I want to create or expose a service of type load balancer to expose my container-based application to the internet or even to a local network. You can specify how this container engine for Kubernetes implements the service of type load balancer. So this configuration you see right here creates an OCI load balancer to expose your application as a service. And this is achieved by creating annotations like you see on top of services like shown in the above example. Now, for those who don't know about OCI load balancer, an OCI load balancer is an OSI layer 4 and layer 7 proxy with support features like SSL termination, advanced HTTP routing policies. It provides the utmost flexibility with responsive scaling up and down. And you could choose a custom minimum bandwidth and an optional maximum bandwidth, both between like 10 Mbps and 8,000 Mbps. So this was about how you can expose your service using OCI load balancer. Now, similarly, there is another option you can use to expose your application where you define the load balancer type to be the network load balancer that will create an OCI network load balancer for you. And the good part about the OCI network load balancer is that it is free. We don't really charge for the OCI network load balancer. And compared to OCI load balancer, and OCI network load balancer is a non-proxy load balancing solution that performs like pass-through load balancing of OSI layer 3 and layer 4 workloads. So we also support workloads like TCP, UDP, and ICMP. So if you have any of that use cases along with OKE, you can consider using that. And our network load balancer also offers an elastically scalable regional virtual IP address that can scale up or down based on what the traffic is coming with. And there is no minimum or maximum bandwidth configuration requirement for the network load balancer. So our network load balancer also provides the benefits of flow high availability. And it also gives you an option to preserve the source and the destination IP address along with the port address. So you have an option to preserve your client IP coming all the way from the internet and going all the way to your application sitting on the OKE worker node. And let's say you want to deploy like a network firewall. So you can also have like a hub and spoke topology wherein your network firewall is sitting in your hub VCN, and which would really inspect that packet for you, and it would be more like an active use cases when the traffic coming from the internet goes to the network firewall sitting in the hub VCN, gets inspected, and only the inspected traffic goes to your OKE network. So all of that really works the same way it works for virtual machines today. So when you expose the service, you have an option to define the Kubernetes specification called as external traffic policy. Now, what is external traffic policy? So external traffic policy is something that really denotes if you want the client IP address to be preserved or not till the very end. So any client traffic, as you can see, coming from the internet, hitting the load balancer, the network load balancer, as you can see, the source IP address right here is maintained. So if you turn that knob in your service definition file and say that I want my external traffic policy to be local, you can maintain that IP address based depending on the use cases all the way till your pods. So let's try to review two different modes or architecture on how you can use it with the network load balancer and understand the benefits. So like I mentioned earlier, this is the first mode, which we call it as the local mode. And like I mentioned, it will preserve that client IP in your HTTP request. And the only thing you need to do is specify this particular line in your service definitions of Kubernetes. And what we really do under the hood is we configure the proxy rules on the worker nodes for a specific node port between some particular ranges that I cannot disclose. And that is only for the pods. So that particular port range, as you can see, will be only for the pods that are local to this particular node. Now, let's say if you have a pod that is sitting on another node and the traffic comes in from and hits this particular worker node, this worker node will never forward the traffic to another worker node. It will only look for the work pods that are local to this particular node. And that is why it is very important to make sure that the way you place your pods or deploy your pods, so that there is no imbalancing of traffic happening. Like you can see, this pod right here would receive 2 times the traffic compared to the pods right here, because what it's going to do is it's going to this particular worker node is just going to look for pods that are local to the particular node. It won't really try to balance the traffic and send the forward the traffic across the worker nodes. So that is where you need to be really careful on how you balance your pod deployment using this particular worker node. And with this architecture, basically any ingress traffic must land on the nodes that are running the corresponding pods for that particular service. Otherwise, your traffic would be dropped. So let's say if you don't have a pod at all and you configure it to be a local mode, the traffic would still go to the worker node. And it would be like, okay, fine, I don't know. I was expecting a pod to be sitting here, but I'm still going to forward the traffic to that particular pod. And if you don't have a pod deployed and if you configured this particular local mode, your traffic could be dropped. And this happens because this particular network load balancer right here, it is not really aware of the pod placement in a Kubernetes cluster. It assumes that each backend or each worker node has that respective pods to receive that equal distribution of traffic. Because as shown in this diagram, this assumption basically can lead to select pods for an application receiving like more traffic than the other pods. So let's make sure that you have, whenever you're configuring this local mode, your traffic or pod placement is done appropriately. So the next mode is the cluster mode. And in this cluster mode, basically, it's the default type. So if you do nothing in your service definition, it's gonna, the selection, the Kubernetes would basically use this mode as the default external traffic policy for your Kubernetes services. And here, the assumption is that you always want to route the traffic to all the pods running in your services with equal distribution. And you don't really care about preserving the client IP addresses all the way till your backend. So as you can see here, when the traffic comes from the internet, the source IP address gets changed at every hop. So it would get changed one at the network load balancer, then it would be changed at the worker node level, And then the CNI right here changes its source IP address to its own. So any request in this mode can be sent to any worker node, and Kubernetes really handles the traffic to get it to the right place. And this kind of mode basically makes sure that there is a good load spreading of traffic from the load balancer across different worker nodes. So when the traffic is routed to a worker node, the node routes the traffic to a pod, which can run either on the same or the different node. So as you can see in this example, compared to the previous example, the cluster mode, if it doesn't find any pod, it would basically forward that traffic to a pod sitting on a different worker node. And this way, there will not be any black holing of traffic. So that's the beauty of this particular mode. And you don't need to really worry about placing or having the right placement for your pods. So let's move on to the next part. So here, basically, just want to mention that there are customers in OCI that really want to also run non-HTTP based services inside our Oracle Kubernetes. And UDP, as most of you would know, or user datagram protocol, is a low latency protocol that's ideal for workloads such as real-time streaming, online gaming, and Internet of Things. So since we support UDP protocol in our network load balancer, you no longer need to maintain like a fleet of proxy servers in front of your Kubernetes cluster to ingest UDP traffic. Instead, you could use the network load balancer for both TCP and UDP-based traffic. So, for example, there is a gaming enterprise that wants to deploy a UDP-based game server on, let's say, the OKE, and they want to use a network load balancer to load balance the traffic. So the architecture maybe could be looking like you have an OKE cluster, let's say, for example, and you have a node pool of, let's say, Oracle Linux instances, which are powered by ARM-based Oracle processors. So you could have that, and then you could have a UDP-based game server deployed in your OKE, and then expose that service, like I was sharing in the previous example, with a network load balancer. So a game server could also include like UDP-based health probes used as a liveness probe. You could configure that as well. And you could have network load balancer, which is provisioned with a UDP listener, and it is associated with like a single backend or multiple backend sets. And the backend set basically is configured to register its backend and perform like health checks based on using the UDP protocol. So when OKE provisions a network load balancer for Kubernetes type service of type load balancer, you can define the type of traffic accepted by the listener. You could specify this protocol right here and make it explicit that you want to have a network load balancer with a protocol UDP that would create a listener with UDP protocol and accept your connection request. So this is one of the way you could also run non-HTTP based workloads on OKE. So talking about Ingress now. So today, our customers are required to use third-party open source Ingress controllers that are deployed within their Oracle Kubernetes cluster, and it is managed like fully by the customer. You can set up like different open source Ingress controllers like Nginx, traffic on clusters you have created with Container Engine for Kubernetes. So this diagram out here, it just highlights on how an Ingress controller looks and operates today on OKE with the bring your own model. So Ingress controller comprises of two parts. The first part is the deployment, the actual deployment of your Ingress controller pods on various nodes. So I'm going to use Ingress controller Nginx as an example here, but what it really do, the first part does is it deploys that image for you, that Nginx image that contains the binary for the Ingress controller and Nginx. So this is the first part, what it really does. And the second part is nothing but the Ingress Controller service or the Ingress Nginx controller running inside the control plane or the master component. And this service basically, it exposes, it creates a service definition, and it exposes this particular deployment as a service of type load balancer. So this is what we really do today as a support for Ingress. So whenever you, let's say, are deploying an Ingress Nginx controller, we expose your deployment as a service of type load balancer, wherein we'll launch an OCI load balancer for you. And this is the reason we do that is because Container Engine for Kubernetes uses an Oracle Cloud Infrastructure Integration Cloud Provider or a CCM, where a load balancer will be dynamically created with correct nodes as a backend to that particular LB. Now, the Ingress Controller deployment pods that you see right here, the pod 1, pod 2, and pod 3, are deployed on like different worker nodes. And it receives, so whenever there's a traffic coming from the internet, it receives that traffic from the load balancer. This load balancer would make the routing decisions based on the ingress resources that you define in your Kubernetes. So let's say whatever paths you define in your Kubernetes service definition file, it would do the routing accordingly, right? So Ingress Controller then would route the traffic to the applicable pods eventually. So when the traffic comes from here, you have a load balancer that is created by OCI. This OCI load balancer would look for the definition that you as a user defined in your service definition file. The traffic would be routed accordingly based on whatever the definition was. And then the Ingress Controller right here would then forward the traffic to your actual application sitting behind the Ingress Controller. So eventually, just to summarize, the Ingress Controller here acts as both the configurator, wherein the configuration part sitting in the control plane, and the router. So it does both. So this is like a sample service definition that I was talking about, which has, as you can see, it has an Ingress class called Nginx that will launch an Nginx-based Ingress controller. And then it also defines that path-based routing that I was talking about that will send a traffic to a service name called as Docker Hello World service, which is nothing but a fleet of pods deployed on your worker nodes. So this was about bringing your own Ingress controller to use with Oracle Kubernetes Engine. So this is the recent feature that we launched recently in our Oracle Kubernetes Engine, and it's called as the node label selector. So a load balancer node label selector in Oracle Kubernetes, basically, it helps to excuse me, it helps to map the backend. So let's say there's a load balancer, there is a network load balancer, there are 3 worker nodes, and I have 2 services, service A, service C. So what it does is it helps to map the backend or the worker node for each service in an ingress. So let's say if you're using an ingress and you tend to create multiple services or logical clusters, service A, service C, like I was mentioning, each logical cluster or service that is exposed to the customer happens to be created or exposed through a load balancer. So service A basically would create a load balancer, service C would create another load balancer. Now, with more than one load balancer, right, for each service, every load balancer that it creates, right, would have all the worker node as a backend. So that was something that was not really helping earlier. Like, why would you want to add all the worker node as a backend to every load balancer that you create? So in that case, we came up with a solution called as the node label selector, which is like a new configuration option that you could define in your service definition that would help you to enable to select which specific worker nodes on your Oracle Kubernetes engine you want it to serve like as a backend set to any load balancer or a network load balancer that is fronting your cluster. So with node label selector, you can specify a one-to-one or a one-to-many mapping for the backends for each Ingress load balancer. So as you can see in this example, there's an NLB, but here I want this LB set to have only service A and service A as my backend. Although this will be registered, all these worker nodes would still be registered as my backends to the LB, but the LB will not send the traffic to node 2 or node 3 because it's not selected as a backend. I explicitly made sure that I don't want to spend my traffic or waste my traffic to send it on to the node 2, which is not really having my service definition applications. So this is a way you could save some time in processing any updates that happens to to the load balancer, because the load balancer now will not really be doing any updates to all the backends. It would have an option to selectively select which backend it wants to be sending the traffic to. So that's the recent feature that we recently announced. And now the next section is, and the last section is what we have is for the security. So now let's focus on the security for Kubernetes clusters. So today, whenever you set up your worker nodes, your API endpoints, load balancers, or even pods, you have an option to wrap a network security group around the VNIC, around the network interface that has that particular endpoint or LB or worker node or even the pods. So with network security group, basically the same way you use it for your virtual machines, you can define security rules for these OKE resources independent of subnets. So with the help of NSGs, basically you can now create an entire OKE cluster with a single subnet and simplifying subnet management altogether. You don't really need to have separate subnets now with different security list rules to control the inbound and the outbound traffic for your Kubernetes API endpoint or your worker nodes or your pods and even the load balancer, because now these resources would have different security requirements and they don't need to be really have a subnet for each one of them. So now you could have one just single subnet and just make sure that the traffic is restricted between them using NSGs. So that makes up like a efficient way to use VCNs and its resources. So the last section is speaking about private API endpoints. So we have had enterprises requiring robust access control for their Kubernetes clusters to meet their security and compliance needs. So private API endpoints here, it helps them to achieve that by providing an option to assign a private IP address to the API endpoint. And this particular API endpoint is what it resides inside your VCN. It's not an endpoint that resides outside your VCN. It is nothing but like an endpoint that sits like any other OCI resources inside your VCN. This way, customers are not really bound to using the public IP address for their API endpoint. They could simply use private API endpoint and just make sure that the traffic is constrained within the VCN. And private API endpoint, basically, it requires full integration with VCNs. So it's already done. Today, we support that already. In OKE, the cluster worker nodes, pods, and load balancer are part of VCN, but now you could also have this API endpoint also a part of the VCN. So it's more like secure, just the way we have it for LBs or the worker nodes and even the pods. And like I mentioned earlier, you could use VCN routing and firewall rules like NSGs to control even the traffic for the API endpoint. So you could apply an NSG for this particular API endpoint to make it more secure. So that it's, let's say, maybe only accessible from a corporate network only or via Bastion host or any specific SaaS services. So that's the beauty of having private API endpoints. And with that, I think that's pretty much what I had. Okay. So this is my Oracle Cloud console. This is my dashboard where I would generally log into and see the overall status of my configurations in OCI. And let's say if I want to go on to my OKE cluster, I would hit on this top left sandwich button, click on the developer services, and right here, I would get an option to go through my Kubernetes clusters or OKE. So I would just come here and first try to create a cluster. I don't want to do a quick create. I want to do a custom create because I want to show it today how we could do the networking part for our OKE. And right here, the first thing what we do is we give it a name, select the compartment, select the Kubernetes version that we want. I'm going to just select the latest. And as an advanced option, I don't want to go into the details today because it's not the part of networking. The networking part would come as a next step, and that would be the interesting part. So I would come and click on next. And then, as you can see, the most important part is the type of CNI that we select, where it gives me two options called as VCN native pod networking or Flannel overlay. Before I select the two, I want to make sure that my advanced options are expanded. And as you can see, when I select the VCN native pod networking, by default, it disables that option for a user to provide that pod side block, because what it's going to do is it's going to take an IP address from the VCN side block for those pods. While on the other hand, for Flannel, as you can see, once I selected Flannel, it enables that, and it defaults it to the CIDR block that I spoke about in my slide deck. And it also gives the users an option to provide a different CIDR altogether, but it's recommended that you don't really provide the CIDR block, the same CIDR block for your VCN where your worker nodes will be sitting. Otherwise, the routing would be messed up. So for this demo, I'm just going to select the default, and I am going to select my VCN. And the next thing it asks me is to create or select a subnet for the service LB. So I'm just gonna select the LB subnet. Same for API. I mean, I have an option to select the same, but here for an example, I am going to select two different ones. And right here, it asks me if I want to use NSGs to control my traffic. So this is where I can come and I can apply the NSGs for either my API endpoint or my LB, or even any other resources that I want to have. Then by default, like I was mentioning, for all our API endpoints, we just provide the private IP address. So users don't really have to maintain a public IP address to talk to their API endpoint. Now this API endpoint can sit inside your VCN, and you don't need to really worry about assigning a public IP address for that. If you really want to have a public IP address, you can just select on that, and it will just give you a warning that it just makes your cluster accessible even from the internet. So depending on how your security model is, you may want to consider either using it or not using it. So for this demo, I'm not just gonna not do it, and I'm just gonna stick to the defaults and gonna hit on next. I'm not going to use NSGs, so I'm just going to disable that. So the next portion is the node pool. So node pool also pretty much the same configuration, wherein I define the name for my pool, select the version, define what would be my shape and size for this particular node pool. I can play with the number of CPUs or memory I could allocate, select the images, and just select the defaults. But here, as you can see, we really want your worker nodes to be highly available. So what we do is we really give you that option how you want to distribute your worker nodes across AD in a multi-AD region. So let's say if I have a worker node, I want my first worker node to be in AD1, and just select the worker node subnet. And it also gives me an option whether how I want my AD to be distributed across fault domains. So I could here select FD1, FD2, FD3 the way you want across FDs, or you could just leave it and we do that automatically placement in the FDs. So let's say if you don't select a fault domain, we will spread your worker nodes, making sure that it's highly available across the fault domains. And then let's go to C. Now, in the next section, as you can see, this particular pod communication, right, from the networking standpoint of view. Just because I selected VCN native pod networking in my previous step, I get this option in my node pool section to explicitly select a subnet for my pods. If I select Flannel in my previous step, I won't get that option. I won't get that option right here because it forces me to define that pod side block that, like I showed you in my previous example. So this is what one would get when they're selecting VCN native pod networking. And the thing to remember is that the number of pods that you can launch in your worker node per worker node in an OKE cluster for native pod networking really depends on the shape of the worker node. So let's say if you have a shape that has 2 VNICs on it, so the maximum size that you could do is 2 into the number of secondary IP addresses that can configure inside your VCN minus 1. So let's say if the secondary IP address is 32 for the secondary VNIC, I would just subtract it by minus 1, and that would be the number of pods that would be supported in a particular shape. So just keep that in mind. While in the case of Flannel, like I had mentioned earlier, you don't have that limitations. So if you want to have like a high number of pods per worker node, you would better go for Flannel than VCN CNI. Because if you want to increase your number of pods, you need to increase your shape as well to achieve that number. So let's say, so this is where it gives you that option where you can really control how many number of pods you could have per node. So it gives that sweet user experience where you can just drag and drop and define on how many pods you want to constrain in a given worker node. So lastly, it's all about Cotton Rain, the remaining Kubernetes stuff. And that was pretty much what you need to do when you're defining your networking for your Kubernetes cluster. And then at the very end, as you can see, it really selects or shows or reviews whatever networking constructs I chose for my VCN. And right, you can see I've chosen OCI VCN IP native and the pods, and then I would just go ahead and create my cluster.
So for the audience, if there is general interest in knowing more about the VCN native CNI and Flannel, and when would you use which one, and what are the pros and cons and comparisons between these CNIs, and whether you can bring other CNIs or do other networking stuff with OKE. If there is interest in that, please chime in, and we will probably do a follow-up that'll focus exclusively on, like a networking deep dive, if you will, for Kubernetes. Yeah.
Okay, well, if there are no further questions, I'd like to thank Ajay again for this wonderful presentation, Jeevan for all your help and support, and thank you all for spending your time here with us today. So with that, I'll go ahead and conclude our session. Have a great day, and we hope to see you again next time.
Thank you.
Thank you, everyone.